Okay, everyone, welcome to the next lecture. This is going to go over chapter 6 when we talk about waves and electromagnetic radiation. So let's just get right started and talk about the nature of waves. And the first thing that I'd like to talk about is that energy can be transferred in two forms in our world. Either by a particle, basically think of that as kind of like, you're keeping your energy in one little spot and you send it from A to B. And then the other way is the wave. So suppose that you had a domino sitting on a table and you want to knock it over. So that process will require you transferring energy from your finger to the domino. One way to do that would be to take another domino and throw it. So from a standpoint of energy, you might say that if your arm is going to impart kinetic energy to the moving domino, in turn, that would impart some of that energy to the domino next to it and knock it over and go on from that. The other way is you could just line up a row of dominoes and knock over the first, and then it would knock over the second and knock over the third and so on and so forth. Eventually, that chain of dominoes is going to hit the last one, and you'll have achieved the same goal. So you can think of throwing the domino to hit the first one, or the one that you eventually want to knock down, as the particle idea, or you could trigger a wave of dominoes by knocking over one and letting a bunch of other ones hit to finally hit the one that you want. And so that's how energy can be transferred. When we talk about a wave is basically, the definition is this traveling disturbance that carries energy in some form. And you might say, great, well, what does that really mean? Basically, it's a way in which that energy moves through particles. And there's some properties of waves that we should talk about. The first is wavelength, and it's the distance between crests or tops of waves. And I'll show you this in an image on the next slide. On a pond, for instance, the wavelength might only be a centimeter or two, but in ocean waves, the wavelength might be tens or hundreds of feet between crests. So obviously really scary things happen when you talk about distances of wavelengths. Frequency is the number of wave crests that would go by a given point every second. So a wave that sends one crest by a certain point every second is said to have a frequency of 1 cycle per second, or often what is known as hertz, H-E-R-T-Z. So 1 hertz if it had one wave every 1 second. That same idea of the pond, maybe it would have a very high hertz, where there's a bunch of waves going by a certain point every second. But on the ocean, you might have very large waves every few seconds, and so the hertz is a little bit slower. Period. The next is period. It's the time between adjacent waves. And it's calculated as the inverse of frequency, so basically 1 divided by frequency. And so period gets measured in seconds per wave, while frequency gets measured in waves per second. Pretty simple there. The next is velocity, and it's the speed and direction of the wave crest itself. So water waves typically travel a few meters per second, whereas sound waves that you hear right now by listening to me could travel about 340 meters per second. And that's why sound often happens before vision. So you'll see lightning and then hear thunder, although they're the same thing, okay? And the last is amplitude. And amplitude is the height of the wave crest above what is called the undisturbed position. So if you thought of a wave on the beach, think of the regular ocean and then how high the wave gets. That's the amplitude. So let's look at what that looks like in image form, where we have wavelength is the distance between two of the waves, frequency of the wave crests, how long it takes for it to cross this point. This is the crest, this is the trough. The amplitude is how high these waves get, and the velocity is how fast it's going in this direction. Remember, velocity is a vector, meaning it has a directionality to it. And so those were the properties of waves. The next thing, here's just an image of, maybe what we would think of most clearly when we talk about waves. but maybe we don't often think that waves also come in sound waves and many other visible forms of light and non-visible forms of energy. And so we'll talk about all of those, but before we do, let's talk about two kinds of waves, transverse and longitudinal. And so transverse waves are what you get when you have waves where the motion of the wave is perpendicular. So think of what perpendicular lines are. They intersect to the wave direction. So the motion of the wave goes up and down, but the direction of the wave will go left and right, for example. The example here are actual waves in the water, or maybe the wave in a stadium where people stand up and down, but then the person to the left or the right of them continues the wave, if that makes any sense in your head. So not all waves work like this, okay? The other are longitudinal waves, where the motion of the wave is basically occurring in the same direction as the wave. And sound is actually a form of wave that moves through the air. So when I'm talking, for example, my vocal cords are moving air molecules back and forth, and the vibrations of these air molecules are going to set adjacent molecules in motion, which sets the next molecules in motion, and so forth, eventually reaching your ear so that you can hear it. Okay, and those happen to be longitudinal waves. Okay, so here's what that looks like, where the regular, idea of the transverse wave, where we have the wave going up and down, but it's also moving. So the motion of the wave and the direction are going to be opposite. Whereas longitudinal, the motion of the wave and the direction are the same. And that's how sound works, and that's how other mechanical waves work. So hopefully that makes sense in your mind. Another idea is musics. The sound of music. So different sized instruments in a band are going to play different ranges, right? And so like the larger string bass in the back here will play lower notes, while the saxophone might play higher notes. And sound waves that have low frequencies have low pitches, whereas obviously the opposite is true. Sound waves with high frequencies have high pitches. So amplitude also, when we talk about amplitude, it makes the sound wave seem louder or quieter. So a higher amplitude means that the wave is higher. So basically, when you hear something as loud, it's going to depend both on the amplitude of the wave and its frequency. The greater the amplitude, the louder the sound. But similarly, we could hear higher frequency sound waves, so sounds that have shorter wavelengths, as higher pitches, while we perceive lower frequency sound waves with these lower, longer wavelengths. You might experience one consequence of this contrast when you listen to like a symphony orchestra, where you get the highest notes are played by small instruments like piccolos, maybe violins, and the lowest notes are done by these massive tuba and double basses. And so basically, just something that's interesting to think about when you think about, music. Perhaps I certainly don't tend to think about waves as being, what I'm hearing when I'm listening to music. So another interesting is that, humans, of course, use sounds to communicate, but other animals do as well. Some animals have refined the use of sound in such specialized ways that, they almost don't use their eyes at all. One example is in 1793, this Italian physiologist named Lazzaro Spallanzani. He did some experiments with bats, and he established that they're able to use sound to locate their prey. He took bats that lived in this cathedral tower, and he blinded them and then turned them loose. Obviously not going to be okay these days. And weeks later, those bats had fresh insects in their stomachs. And basically what that proved to him is that they didn't locate their food by sight. And so similar experiments were also made, which made sure that they weren't using their ears either. And so today what we understand is that these bats are navigating by emitting these high-pitched sound waves and then listening with both ears for the reflection of those waves off of other objects. and basically this echolocation allows them to fly in complete darkness. So it's basically a really interesting example of how sound is used by all organisms. Let's see. Let's keep moving. Let's talk about this idea of interference, where you could get waves from different sources that might overlap and affect each other. And the first thing that could happen is that you could get two waves that are going in the same direction that actually amplify each other. And this is called constructive or building interference, where they act together. So you get two waves of similar amplitude that then combine to make double the amplitude of the wave. And so that's called constructive, where the wave's amplitude will be additive. The next example is in the opposite way, called destructive interference, where you get two similar amplitude wavelengths and waves going in the opposite direction of each other, and they cancel each other out, and so you then hear nothing. So basically, this idea of interference is kind of interesting when you think about why certain things might sound louder and why you might not hear things on the other side of another object. So basically, if you take away that the cross, what's happening here between constructive interference and then of course cancellation, that's really all I need you to take away from it. Here in this image, you'll see the two waves that are originating from different points. They create an interference pattern where these bright regions correspond to constructive interference, while the darker regions, you can see here, as it gets darker, that's basically showing the destructive interference. So kind of interesting, really, when you think about basically how waves can interact with each other, and we're not being able to see this. So to actually see it visually kind of helps to understand what's going on. So now let's talk about the electromagnetic wave. All right. You might have maybe gone to the dentist recently and had your teeth x-rayed, or maybe like me, to get through college, you cooked a lot of meals in a microwave oven, or maybe you just turn on the radio. And in any of those situations, you're going to have firsthand experience with the phenomenon known as electromagnetic waves. So basically, all electromagnetic waves have the same velocity. It's the speed of light, but they won't have all the same energy. And in fact, what we can see when we talk about lower frequency is going to have red color, and higher frequency will have a blue color. And you'll see that in a second when I describe the visible spectrum on the electromagnetic spectrum. But basically, let's talk about, before we talk about the entire electromagnetic spectrum, let's talk a little bit about transmission, absorption, and scattering. And the best way to talk about that is to first start with transmission. The only way that we can really know about electromagnetic radiation is because we can observe it with our eyes. That's how we started off. All of these electromagnetic rays we're going to talk about interact with matter. Our eyes are the first example. So our eyes interact with visible light, and that visible light sends nerve impulses to our brain from our eyes. Those impulses then get interpreted as what we see. So when an electromagnetic wave hits matter, one of 5 processes can take place. The first is transmission. The wave often just passes right through that matter, as does the light that passes through the window or Earth's atmosphere. That process is called transmission. So transparent materials are not going to affect the wave other than slowing it down a bit while it's in transit. So that's what transmission is. So the fact that you can see out of your window is because light is able to transmit through it. The next is absorption. And absorption is basically the opposite of that. So you could think of matter like an asphalt driveway on a summer day. It's probably going to soak up the wave and its energy, and that process is called absorption. The energy of absorbed electromagnetic radiation gets converted into some other form of energy. And so what do you think that is on an asphalt? It's the heat, right? So that asphalt gets super, super hot on that really hot day. So black color and other dark colors absorb visible light. So that's one reason why if you maybe step on your sidewalk, it's a little less hot than the really dark asphalt. Okay. The next is scattering. Alternatively, scattering of electromagnetic waves is what happens when they're absorbed and then rapidly re-emitted in this process known as diffuse scattering. Most white materials like a wall or maybe the piece of paper in front of you are going to scatter all wavelengths of light in all directions. And that actually plays a really big role in controlling Earth's climate because things like clouds and snow are going to scatter the wavelength coming from the sun. So basically, if you have a colored object, like a red sweater, and you see it as red because the light that's scattering off of it is primarily coming into your eye as in red wavelengths, while it's absorbing light in the green wavelengths. And so that's kind of interesting to think about why you're seeing colors is because of this scattering. The other thing I'd like to talk about is reflection. So why do we have objects that are reflective like mirrors? That's because they scatter visible light at the same angle that the original wave comes in. And so that process is called reflection, and that's why you see an actual mirror image of what is coming into it. And so that's kind of interesting to think about why you could actually see yourself in a mirror and not really see yourself when you're looking at a different object, because different wavelengths get refracted. So here's this example of refraction where we have the pencil going into this cup of water, and the wavelengths are not coming out at the same angle. And so you'll see the pencil going in at this angle, but then it looks like it's going in at a different angle when it's in the water. Now, similarly, you can see as visible light would come into this prism, it gets refracted, and you can start to see all of the visible wavelengths coming out of this original visible light. Here's this example that I talked about of black asphalt absorbing the energy from the sun and converting it to heat, and that's why it would get very, very hot on a summer day out here in the desert. There's just an image of clouds as an example of a bright white object that would diffuse the scattering of sunlight, and then an image of a mirror. And the reason why this mirror is in this fun house is because this mirror itself is actually bent, not because there's anything going on with the wavelengths coming in. So finally, I'd like to talk about the electromagnetic spectrum as a whole. And what I want you to notice here is that we have everything from gamma rays, which are extremely dangerous, to radio waves, which last time I checked aren't very dangerous. In fact, they're not dangerous at all. And what is different between these things, between those two types of rays, are both their frequencies and their wavelengths. And I want to point out that the frequency, or the hertz, which is measured in hertz, as you go towards gamma rays, that number gets very, very large, where this frequency is increasing. And as you get down to radio waves, the frequency is much less, only 10 to the 2, as compared to 10 to the 24th for gamma rays. Where on the other end of this spectrum, wavelength is in the opposite, where the wavelength is very, very small when it comes to gamma rays, but large when it comes to radio waves. And so those properties lead to the differences between something like a gamma ray or an X-ray being much more dangerous than radio waves or even microwaves. But notice how quickly that these waves become dangerous to you, where we go from radio waves, something like 10 to the 8th, all the way down to 10 to the second, uh, being totally harmless. But once we get into microwaves, I don't think you want to stand in front of a microwave emitting microwaves at you for very long. Um, Neither would you want to stand in the path of ultraviolet radiation, which, if you know much about ultraviolet radiation, where does that come from? You get it a lot from the sun, and that's why you want to make sure that you're wearing clothing and obviously wearing sunblock. And so that's just something to keep in mind, is that what makes these wavelengths quite different is their frequency as well as their wavelengths, but in different ways, I guess I'll say. Now, notice right in the middle this very small section between ultraviolet radiation and infrared radiation, both of which we are unable to see, correct? You don't see the ultraviolet radiation coming down from the sun, and you don't see infrared light when you've used things that might have infrared light. But you are able to see all of the visible spectrum, which is this very small, in terms of the entire electromagnetic spectrum, piece of all visible light, starting from the violets and going on to the reds in that sort of Roy G. Biv spectrum. But notice as the wavelength decreases, we get closer to our blues and our violets, and as the wavelength increases, we get our reds and our deep dark, I guess you would call that plum color. But basically, red it occurs with with longer wavelengths, and the blues and the greens come from shorter wavelengths. So I think that's all I'm going to talk about for this electromagnetic spectrum. Let's talk a little bit more about radio waves and microwaves, just a little bit more in depth. Radio waves range from kilohertz, which is 1,000 cycles per second, to maybe several hundred megahertz. And then they are the longest waves. And then coming down from that, we have our microwaves. And microwaves have a range of about 1 meter, which is only obviously a few feet, to maybe much less than 1 meter. And so microwaves are very short range, whereas radio waves, you probably are aware, have very long ranges, so where you can hear them from cities away. And there are also things called shortwave radios, which have spans of countries and across oceans. And that shortwave radio is just on a shorter frequency than normal AM and FM. So that's kind of interesting to look into if you're interested into that shortwave radio. The stealth fighter is an interesting piece of technology. It's actually been engineered to be able to reflect and absorb microwave radiation, and that makes it unable to be detected by radar. So that's kind of an interesting way in which we've used this electromagnetic spectrum for our own good, I guess you could say. Let's talk a little bit about what AM and FM radio transmission is. So AM and FM radio are different frequency modulation. And modulation is the technical term that is used for adding information to a signal, which is the wave in this case. So basically, think of it like this. If you had to send a message across a lake with a flashlight at night, you could take one of two strategies. You could send a coded message by like turning the flashlight on and off, and that would be like you varying the brightness of the light. Or alternatively, you could change the color of the light by passing blue and red filters in front of the beam. So radio stations kind of adopt those two similar strategies. All stations will begin with this carrier wave that you see right there on letter B. And that carrier wave is this fixed frequency. AM stations typically broadcast between 530 and 1600 kilohertz, whereas the carrier frequencies of FM usually range from 88 to 110 megahertz. So the process of amplitude modulation, which is AM, just depends on varying the strength, which is the amplitude, of the carrier wave according to this sound signal that's going to be transmitted. And so what you get is at C, this modulated signal that basically changes the wave, and it takes the shape of this sound wave that gets impressed on that regular carrier signal. So when that signal gets taken into your radio, the electronics inside are designed so that the original sound signal is comes across your radio. Um, and basically one reason why in which you can hear AM frequencies uh, farther than you can hear FM frequencies is because AM frequencies are easily scattered off layers of the atmosphere, and they can be heard over larger distances. So hopefully that makes sense as to how these waves get modulated to carry a signal to your equipment so that you can hear it. Here's just another example, obviously, that I talked about using microwaves that travel much smaller distances, but then change once they hit the object that you're trying to heat up, and change that energy from this electromagnetic wave into heat energy, and heat up your microwave dinner. I guess that's what people use microwaves for. The last thing is infrared radiation is something that's kind of cool to talk about. IR radiation includes wavelengths of electromagnetic radiation that are going to extend from a millimeter down to about a micron, which is 10 to the negative 6 meter, and that's what that letter that looks like a U, it's actually called mu, and it means micron. Our skin can absorb infrared radiation, and it provides this crude kind of detector. You would feel infrared radiation when you reach your hands out when you have a fire, and so that's why it feels warm. Or you could feel your stove being hot if you had a gas stove, and so we feel infrared radiation as heat being emitted. But all warm objects emit infrared radiation. It's the reason why if you touch your forehead, you'll feel warm. It's because you're emitting this infrared radiation. Um, Infrared radiation is thus used by, I guess, science and all sorts of military uh, crafts to basically detect living things, or warm engines at night, depending on what you're trying to see. So here's an image of this elephant that this photograph is taken in the middle of the night. But if you have the equipment and able to see heat signatures coming off because of this infrared radiation, you can see that this elephant is very, very warm in places where it's red, and cooler in places where it's blue, whereas the surrounding environment is very blue. And this is called its heat signature, and it's just the heat escaping from the elephant based on this infrared radiation. Um, let's see, anything else to talk about there? Probably not. So the last is that visible light, which has the range of 700 nanometers to 400 nanometers, and these colors are basically slices of the electromagnetic spectrum. What I said, where when you looked at that glass prism, it was able to separate light, which is all of this combined together is basically bright white light, and different wavelengths come bend out of that prism, and then you get to see what we perceive as visible light, as this basically rainbow, which is a sequence of the colored bands. Um, the relative sensitivity of your eyes can differ for different wavelengths. Some people are very perceptive of certain colors, and some people don't have the actual equipment, I'll just call them for this class, to be able to perceive certain pinks or wavelengths. So some people can see, yellow, whereas others might not see yellow. Some people have trouble seeing reds and greens, depending on a number of different changes to the actual mechanics of your eyes, and not have anything to do with the spectrum. The spectrum is the spectrum. So here's a thinking question for you. Why does visible light travel through clear glass and why doesn't it travel through metal? What would be the reason for that? Um, and I'll let you think about that while we continue the rest of this. And there's only a few more slides here. But here's, again, just an example of that prism separating white light into the visible spectrum. Here is what the eye looks like, and just in case you were curious, where you have a bunch of cones and rods, and this is what helps you pick up and basically be able to send a signal along the optic nerve to your brain, which then the brain then interprets what that signal is, what you're looking at, and what color it is. So pretty interesting stuff to talk about. I've seen different talks about different amounts of cones and rods and being able to pick up certain colors. So if you've ever looked at birds who might have bright iridescence on their feathers, what's interesting is that birds have many more cones and rods than we do, especially to pick up these iridescence. So things like, think of a peacock that's really beautiful. I can't imagine what that would look like to a peahen. It would just probably look incredible. So just something to think about there. The last that I'd like to talk about, well, maybe we'll talk about two more. Ultraviolet radiation. UV radiation is in the range of 400 to 100 nanometers, shorter wavelength with more energy, and it can start to do damage to your cells. And that damage to your cells, basically, it can actually change your DNA. And obviously, what happens there is a lot of cellular damage. Obviously, when you talk about skin cancers and other types of cancers, is because of changes to the DNA. The big problem here is obviously the sun producing these intense ultraviolet radiation waves in both longer and shorter wavelengths. But fortunately, our atmosphere will absorb a lot of that harmful short wavelength, and it shields all living things that obviously all live outside. But obviously, if you're going to spend a lot of time outdoors under the bright sun, protect your skin with either sunblock or usually sunblock, but if not, hats, and you've all heard this all before. So X-rays. What are X-rays? X-rays have a range of 100 to 0.1 nanometers, very high frequency. What are they used for? Well, mostly in medicine, where of course you've probably all had X-rays taken before, and they have this high frequency, and because of that, they're very high energy, and they can penetrate really several centimeters into most solid matter, but they are absorbed to different degrees by all kinds of materials. And so that fact basically allows doctors to take images of bones, teeth, and basically it's the reason for that is those bones and teeth will absorb the X-rays more than the skin or the muscle surrounding it. So you get these detailed pictures of inner structures. And so that's what an X-ray is. And then the last one is gamma radiation, or gamma rays. Gamma rays are the highest energies in the electromagnetic spectrum. And in gamma rays, everyone likes to think about maybe like the Incredible Hulk, who was made from gamma radiation. Unfortunately, not as interesting in our world, because it would just kill you. They're normally emitted on Earth only in very high energy nuclear and particle reactions, but they are produced abundantly in distant stars. So there's gamma radiation out in space for sure. Gamma rays actually do have many uses in medicine. Some types of medical diagnoses involve maybe giving a patient a radioactive chemical that emits gamma rays. And if that chemical concentrates at places where bone might be healing, for example, the doctors can monitor the healing by locating the places where those gamma rays are emitted. But obviously, there's a lot of danger in that as well. They can also use gamma rays to treat cancer. In those treatments, the high energy gamma rays are directed to tumors or other malignancies that can't be removed surgically. And if the gamma ray energy is absorbed in those tissues will die, obviously, and the patient has a better chance to live. Unfortunately, it could also get absorbed by healthy tissues, So pretty dangerous. Um, Gamma rays also are used to like find weaknesses in building materials because they just penetrate things very, very strongly. You could think of them as like super X-rays almost. They're also used to study astronomy because many of the interesting processes that are going on in our universe involve bursts of very high energy, and so you actually can pick up gamma rays when we look out into the cosmos. And so, with that, I think I will leave you here with our talk about waves and the electromagnetic spectrum. Let me know if you've got any questions on this, and I'll see you in the next chapter.